right, welcome to this explainer. Today, we're going to put on our detective hats and crack a really fascinating case. How in the world do computers actually understand the grammar of code? We are diving deep into syntax analysis. So, let's start with a mystery. A computer gets a line of code, something like A plus B times C. Now, you and I can look at that and say, yeah, that makes sense. But how does the machine know? How does it figure out that the structure, the grammar, is actually correct and not just a random jumble of symbols? Well, the answer is hidden inside the analysis phases of a compiler. Our investigation today is zeroing in right here on phase 2, syntax analysis, which we also hear called parsing. This is the critical stage where all the grammar rules get checked, and it's exactly what we're going to break down. Okay, so to solve any good mystery, our detectives need some clues, right? Before we can even think about checking the grammar of a sentence, we first have to figure out what the words are. Let's break this down. The whole process kicks off with the lexical analyzer. You can think of it as the field agent on the case, grouping all the raw characters into meaningful words. We call them tokens. But it's our lead detective, the syntax analyzer, that takes those tokens and figures out if they actually form a grammatically correct sentence. And this image right here shows you exactly why we need these two different specialists. The lexical analyzer, it's pretty powerful, but it's got its limits. It handles something called regular grammars, which are great for spotting simple patterns like variable names or numbers. But, and this is a big but, it can't handle complex nested structures. You know, like making sure every single opening parenthesis has a matching closing one. For that, our detective needs a much more powerful tool, this syntax analyzer, which understands these more complex context-free grammars. So, let's properly introduce our detective, the parser, and see exactly how it goes about conducting its investigation. Okay, if we follow the evidence here on this flowchart, you can see the source program first gets fed to the lexical analyzer. It chops it up into tokens. Then it sends this stream of tokens one by one over to our parser. And that's when the parser really gets to work, checking the grammar and building the central piece of evidence in this whole case, the parse tree. So what is a parser exactly? Well, it's this piece of software that takes that stream of tokens and tries to build a data structure out of it, usually a parse tree. This tree gives a really clear structural picture of the code. And here's the kicker. The very fact that it can build this tree is the proof that the syntax is correct. So the parser's mission is really 4 things. 1, it verifies the structure. 2, it builds that super important parse tree. 3, if something's wrong, it reports the syntax errors. And 4, it even tries to recover from those errors to keep checking the rest of the code. So it's not just a checker, it's a builder. And this is where the magic really happens. This is our detective's big aha moment where a totally flat line of code gets transformed into this rich, meaningful structure. Let's actually watch it in action. Our piece of evidence is a simple little expression, ID times ID. Now, in compiler speak, ID is just a token that stands for an identifier, like a variable name. So you can imagine this is something like price times quantity. Now, watch how the parser builds this thing from the bottom up. In step 1, we've just got the raw tokens, but by steps 2 and 3, it's already starting to group them. It recognizes that an ID can be considered a factor, and that factor can be a term, all based on the language's grammar rules. And the process just keeps going, building upwards. See, in step 5, the parser connects the 2 identifiers with a multiplication sign, forming a bigger term. Then finally, in step 6, the whole thing, the entire structure, is recognized as a valid expression, or E. And there you have it. The case file is complete. This final tree doesn't just prove that the original code was grammatically correct. More importantly, it gives us a clear, unambiguous structure that the next phases of the compiler can actually work with. Now, what's really cool is that our grammar detective doesn't just have one way of working. There are actually 2 main strategies it can use to solve the case and build this tree. This visualizes the 2 methods perfectly. Top-down parsing, it's like a detective starting with a theory. I believe this code is a valid program, and then trying to find evidence to match. Bottom-up parsing, which is what we just saw, does the complete opposite. It starts with all the evidence, the tokens, and builds upwards to see if it can form a coherent theory. And under these 2 big approaches, you've got all sorts of specific techniques. For top-down, a really common one is recursive descent parsing. And for bottom-up, one of the most famous is shift-reduce parsing. They both get to the same result, but they take fundamentally different paths to get there. So, after all this detective work, what have we learned? Why does checking the grammar matter so much in the grand scheme of things? You know, this quote really hits the nail on the head. The parser's work is so fundamental because it creates the structural foundation for everything that comes next. That parse tree, or a slightly fancier version called an abstract syntax tree, becomes the map that guides the next phase, figuring out the program's actual meaning. Really, you can think of it as a bridge. On one side, you've got this flat list of tokens. They're just words. But once you cross the bridge of syntax analysis, you have a rich, hierarchical structure. It's the exact moment where code stops being just text and actually starts becoming a program. But closing this case immediately opens a brand new one. Just because a sentence is grammatically correct, like the classic example, colorless green ideas sleep furiously, doesn't mean it makes any sense. Which leads us to our final lingering question. Okay, the syntax is valid, but how does a computer understand what the code actually means? Well, that is a case for another day.